happen, but what actually ends up happening that makes the thing work. And we're talking about how the optimizer actually does all the stuff. Some of the elements are still true, some of the elements have evolved, and I'll say a little bit about some of the evolution today. Just to remind you, Project 3 again is due a week from Thursday, so you've had a relatively long amount of time for that. That's the B tree project, B plus tree. Again, emphasis that you can use your old Project 2 solution or you can use ours, and don't think that it's exactly the same as RBFM. Neither the leaf nodes nor the non-leaf nodes of the B tree are the same as the records that you used in Project 1. The hard part basically of this project is dealing with having to do splits, B trees when you do inserts, doing the splits which may recursively propagate up the tree. That's the part of this project that ends up being the most interesting to be able to work through to make it work. And for deletes, you can do a relatively lazy delete. If you delete a record, it should not show up, but you don't have to do the merges to do the delete. You don't have to do the stealing or the merge. It's okay to have something where the deletes end up having pages where you could merge them together and they don't have half the size that they should have. Normally we want to have every page having at least half the maximum that it could have, but you don't have to do that unless you want to do the extra credit, which is quite a bit harder than you might think. Let's see, I expect to be able to return the Project 2 grades to unmute those today. I actually expected it over the weekend, but there's a little bit of discussion going on some elements of the grading, but I definitely expect that to happen today. I thought it would happen over the weekend. You know about the midterm. If there's anybody who hasn't picked up the midterm yet, please pick up the midterm for me at the end of the class. And reminder that I will have time today, I will end up being available if folks want to be able to come by. I actually will probably be around between 2 o'clock and 5 o'clock if people want to come by and ask me questions. I'll be happy to talk to you about your exams, and we'll see about whether or not the grades should change. I know there are a lot of people who want to ask questions about that. You can also ask Saloni in the labs, but it would be important for you to ask the questions by the end of the week. Okay. We talked about estimating cardinality. Again, the optimizer has to be able to figure out what's a pretty good plan. Despite the name, it won't be the optimal plan, it'll be a good plan. And there are all sorts of statistics that are maintained, and they're not maintained all the time, even in memory, about what the size of the relations are, or the number of different values that you have in some particular attribute, or things like the low and the high value that exist, or the number of index pages. And again, you can look at the catalogs of any system. Basically you can see how many different catalogs there are. You can look up for Postgres or for Oracle or for DB2 or SQL Server or MySQL or whatever. There's a huge number of catalogs that are kept with all kinds of information that helps deal with questions of security and performance and just being able to try to do stuff about optimization. An immense number of things that are kept, but they're not fully kept up to date all the time. And there could be more. There could be things saying this plan has worked out better than I expected and this thing is worse. There's learning that goes on in optimizers. There was work on this that goes back nearly 10 years on learning optimizers, and there's a lot more work going on at places like Amazon on playing with the use of learning. When you have enough cycles, here's an example of something you can do. If there are a couple of different plans that you have, you could experiment and see what would the performance have been if I had done this other plan. Or let's run 2 plans and see which one finishes first. Or a whole range of different things you can do playing with this kind of testing. Or maybe I'll mostly run plan A, but I'll take 1% of my customers and I'll run with plan B. And as long as plan B seems to be good or maybe better, I'll see about switching over more of my customers to B. So old concepts about optimization are being changed as people have more cycles and systems. You don't want to waste time thinking about all the plans that are possible because the number is huge, but at least thinking about different alternatives and learning what works well, that is a field where there's a lot of interesting work going on. We looked last time at what happens when you have simple selection and range predicates. Basically, we're going to assume that when you have equality, if the number of different values is this pi sub a of r, that is the number of values you get, the absolute value stands for cardinality of. So the number of different values you have in attribute A, so you project on A, and you see the number of different values that you get. So we'll assume that, if there are 100 values, that everybody gets 1/100th. If there are 10, everybody gets 1/10th. That's bogus, and we'll talk about simple ways that that's been improved for the last 20 years in this lecture with things about histograms. Because not everything's the same. If you have 50 states, you don't have 1/50th of the students from each state attending UCSC. There are people from all sorts of states, but there are more people from California. But that's a simple way of doing it. And we talked about, and I will again remind you, I never changed this because it's important to remember that this formula is wrong. It's also in the textbook, and it's wrong, right? But I keep thinking, am I going to change it? Nah, I'd rather explain why it's wrong. We talked about this last time. The right value, the number of values between low and high, is actually, if you're going to be precise, high minus low plus 1. So the number of values between 1 and 100 isn't 100 minus 1. It's 100 minus 1 plus 1. The number, and also if I'm looking for people who have ages that are in the 50s, the number of people who have ages in the 50s isn't 59 minus 50, which is 9, it would be 50 minus 50 plus 1. So the percentage, if there are 100 different values from 1 to 100, the number of people who have ages between 50 and 59 would be actually 10. So again, that val 2 minus val 1 should be plus 1, that high minus low should be, plus 1. So that's what the stuff is going on. So this again is wrong, and we've discussed what the right answer is. We discussed it last time. Just reminding you about it, because I hate having slides that have mistakes on them, but I've never corrected this one. Although every time I give this course, I emphasize that it's wrong. Okay, so now there is an assumption which is hard to fix. There are things that can be done. The assumption is that when you have two predicates, a conjunction of two predicates, P1 and P2, that they're independent. Oh, and I forgot to, anybody need the microphone? Okay, I forgot to put it on. Unless somebody asks me to, I'll leave it off for today. So if you have two reduction factors, we'll assume that they're independent of each other. So if one thing is 1/10 of the tuples and the next one is 1/2 of the tuples, then we'll assume that the conjunction of them will apply to 1/20th of the tuples. And again, if you've taken probability, you know that this is the independence assumption, but things aren't necessarily independent. So if you're even selecting people where age equals 21 and gender is M, maybe these things are independent of each other, but maybe they're not. For example, if you're selecting computers where the major is electrical engineering and gender equals M, well, the number of women in electrical engineering, actually hasn't gotten that much better over the years. It's improved, but there are more electrical engineers who are men. So the independence of those two predicates is highly, highly questionable. But what are you going to do as an alternative when you have all these different combinations of predicates to consider? Unless you're going to keep track of some interesting predicates and what the situation is for those. And again, there are systems that do things now because there's a lot more CPU available, and especially when you're running the same query, a lot of times you can learn about doing good things about it. But you'll remember from 180 that sometimes you have parameterized queries, where value equals $x, and depending on what $x is, whether they're asking for age equals 21 or age equals 72, whether they're asking for state equals Hawaii or state equals California. There are different things that are going on. Are you going to keep things for every different parameter? Well, maybe, and there are systems that try to do variations of that. The simple assumption that was made in System R, and variations of this are still used, is that if you have a negation of a predicate, where the negation of something is true, well, everything has to be either true or false. We'll assume that we don't get unknown. And so the probability that not P1 is true is 1 minus the probability that P1 is true. So the reduction factors are going to be 1 minus the other. So you have, where age not equal to 21, you'll take 1 minus the probability that age is 21. And if you have a disjunction, an ORing together of predicates, and those do happen. In, by the way, is a disjunctive predicate. right? In set, computer science or electrical engineering, that's an or, even though it looks like an in. And what you do is, again, based on independence, you'll basically say, take the reduction factor of P1 and the reduction factor of P2, but subtract, because you've counted it twice, the probability of both happening. So if you look at the Venn diagram for union, P1 and P2 happening is counted twice. If you take the probability for P1 and the probability for P2, since you only want to count it once, you subtract again. If you've taken basic probability, you should see how that ends up working. So RF P1 counts the case where P1 and P2 are true. RF of P2 also counts the cases where P1 and P2 are true. So to be able to get the value, you subtract basic probability. You subtract the thing that's double counted. That's how that works. Okay. Now this is one which, again, I'm going to have a hell of a time justifying. I've taught this a lot of times. It's really in System R. I can't fully justify this one. There is variations of it are used now, but you have joint predicates. Joint predicates are really important. How much does the joint factor predicate filter the results? So suppose that you have A join B, or R join S, where you're saying the joint column of A equals the joint column of B. Well, if you took the full Cartesian product, then you'd go ahead and you'd get the number of things in R times the number of things in S. How much does the joint product reduce that? Now there could be other predicates too, predicates on R, predicates on S. That would reduce the result too. But the question is, we know how to deal with those, at least we've talked about how you do it. How do you reduce by this join predicate? How many things have matches? And so the assumption is, and this is usually, but not always true, the assumption is that it's a primary key foreign key. And by the way, it doesn't have to be just on one column, it could be on multiple columns. So you're looking for, you're doing something where you're taking students and majors. And so we're basically assuming that students have one of those majors, that it is a foreign key. The majors that students have are the majors that are listed as a list of majors. But basically, the assumption is that because it is a foreign key, if you look at the values of the join column of one relation, it's a subset of the join columns of the other one. And that's going to be true if it's a foreign key, if you have referential integrity. Okay. So the general idea is that, again, you're going to assume that the value set that you have in the smaller table is a subset of the larger table. So, for example, if you're looking for students and departments where students major in the department, you're going to end up dividing by the larger number of the values inside. So, in particular, if there are 10,000 students, you're going to assume that you end up getting a result where you take 1/100th of what's going on, because there are only 100 majors, and each major is going to have the same number of students in it. So if I'm doing the join and I'm looking for things, I'll assume that I'll find a match where each major has approximately the same number of students in it. Now again, this is an extremely ridiculous thing to try to justify, because there could be majors that nobody's actually enrolled in, right? It assumes uniformity. So it could be that the university used to offer underwater basket weaving, but nobody's taking that anymore. But in general, if the university has a major, there are students who are enrolled in it. So we have our ugly friend uniformity sticking here, but the assumption is that the 100 things that end up existing in the match. And the same principle then, again, when you take the maximum, not of the relations, but the number of different values in the column. And so that's the thing that ends up being assumed. And again, it's very, very hard to seriously justify. We're finally going to do something where we'll talk about something that is in standard usage, in fact, way beyond what I'm describing here, to be able to not have to have all these uniformity assumptions, and that's the notion of a histogram. As I said, there are more students at UCSC who are from California than there are from Hawaii or Kentucky or Maine or any of those states. So again, in reality, uniformity is bogus. And so if you're looking at the cost of doing the query, if you're looking at the California students, you're gonna get a big answer, you're gonna have an expensive thing to do. If you're only looking for the people who are coming from Kentucky, there won't be that many students. The query may end up having a lower size, it may be cheaper to compute. You just, when you look up the people from the state, you'll find fewer people, okay? So we're gonna talk about how histograms can help you do this. And by the way, just as a fast aside, and the only justification I can give for this is that it didn't work badly. System R had this interesting problem. Remember, you don't have statistics about everything. You may not have statistics that you've kept about how many different values you have in this particular column. So basically, if you have an exact match query, in the absence of any statistics, System R scratched its head and said, I'm gonna pull a number out of nowhere. So the number that it used as the reduction factor was 1/10 when it didn't have statistics. I can't justify it other than it worked semi-reasonably at the time, and you have to do something. Okay. It would be possible to actually learn what the value is over time, and again, background things compute a lot of statistics, right now. And when you have a range query and you don't know what the low and the high value are, what value did you use? Again, there's a principle here. This is one of the reasons I talk about this. Engineering basically takes impossible problems where there isn't any solution and finds something that semi-hammy-demmy sort of works a lot of the time anyway. It's not about getting it right. Yeah, you'd like to be able to get it exactly right. Yeah, you'd like to have a system where all the statistics are available. Sampling, as I mentioned, can be a good way to get statistics in a lot of cases where it might be too expensive to keep counting, and sampling can end up being cheaper, and there's a lot of stuff that goes using statistics, using sampling, and there's a lot that goes on using learning. But the point is, if you don't have anything to use, you try to pick something, you try to see whether or not there's something better, and you just go with it because you don't have any choice. I mean, you can throw up your hands and say, I'm not gonna optimize this query, give me statistics. That's not a really good answer. 1/3 and 1/10 work semi-decently at the time, okay? But what can be done to get rid of this uniformity assumption in a reasonable way, in a way that isn't ridiculously expensive? Here's a simple thing that is in common usage, variations of this. What you can do is you can keep track of the most frequent values and have a better idea of how many times those show. So for example, if it turns out that, let's say, 9/10 of the students at Santa Cruz are from California, keeping track of that could end up really making things better. You also might keep track of most frequent values. At one point, there were things only keeping track of the, couple of most frequent values. Now you might keep track of the 20 most frequent values. It might keep track of all sorts of different values. And again, you won't keep this up to date all the time, but you'll try to do something better than having this dumb uniformity assumption, okay? So the histograms help you get better factors about what the reduction factor is. Yeah.
I'm just a little confused as to what values exactly mean. So is that like the result?
Number of different values in a column.
Okay.
Here we're only on the number of different values in the column. What's happening is we're using a mediocre statistic to try to use incorrect cost formulas to figure out an approximate size of the result. And again, a lot of these things propagate errors in all sorts of different directions. Improving this is an important industry. People spend a lot of time on optimizers trying to improve it. So we're talking about base values. The number of different queries that people come up with is huge, and there are all sorts of ad hoc queries. You might spend a lot of time trying to optimize very commonly used queries. Then somebody's going to throw a new query with it, or a query with a new parameter at you. And so the whole idea of what we're doing here is showing how you can build up out of things to come up with a reasonable way of figuring out cost and size and finding the best plan. Remember, two things. Number one, the size has to be the same no matter what plan you use. You want a formula for figuring out the size, where the size that you get is the same value no matter what plan you use, because if you're getting A join B join C with a bunch of predicates, it's the same thing whether you do CBA or CAB or any of the other combinations. The cost, of course, is going to end up being different. And again, what are we doing with optimization? Are we trying to find the exact cost of executing the query? Well, that would be nice. But the real point is to avoid the bad plans and actually these days find a pretty good plan. If the cost that you find and you estimate that the best plan costs, 200 and it actually costs 350, but it's still a darn good plan, even if it's not necessarily always the best, that's okay. You want to be able to find a plan where you expect it's going to be good and you're right. So that's a general idea here. So we'll talk about two different kinds of histograms. We'll talk about equi-width histograms and equi-height histograms. We're going to start off with width, okay? And here's the idea. And don't confuse this with hashing. This isn't hashing. The term bucket is used, but this is not hashing, okay? So what we're going to do is we're going to go ahead and we're going to look at ages of children. And we're going to split the domain into some number b. It's not a block size, it's just a number. B is for bucket. It has nothing to do with hashing, and it's not a block size, it's just the number of buckets. We're going to divide the domain into b buckets that have equal width. So in particular, if we're looking at children between 1 and 16, I guess 0 didn't get counted. We're looking at children whose age is between 1 and 16. What we're going to do is we're going to have 4 buckets, and each of them is going to have the same width, so 4 times 4 equals 16. So we're choosing to have 4 buckets. Could have chosen to have more than 4 buckets. We're going to have 4 buckets, and each of them is going to have equal width. And basically what we're going to do is we're going to say, okay, the first bucket is 1 to 4, the next bucket is 5 to 8, which of course is just 1 more than 4. The next bucket is 9 to 12, the next bucket is 13 to 16. And we'll count how many children have ages that fall into each of these 4 buckets. And you'll notice that the number is different. For this particular database instance, there are going to be 27 kids whose age is between 9 and 12. There are only going to be 5 whose age is between 1 and 4. So we'll figure out how many people fall inside each side, and this is going to help us get better estimates than we would have gotten if we assumed that every age was uniform. It doesn't give us the exact value for each. Remember, normally there are a whole lot more than 16 different values, and yes, you can keep track for each value of what's going on, but that actually gets done these days more than it used to be. But if you have something where there are salaries, I'm not going to keep track of every single value of salary, including 2 cents, 7 cents, etc. Or time. I'm not going to keep track of each thing. I'll keep track of a range of things. So what does that allow me to do? Basically, I'm going to make a pass over R to construct an accurate equi-width histogram. How do I do that? Well, I know that in this particular case, the number of kids that I have, basically is going to be, let's see what that is, 40 plus 19 is 59 plus 5. There are 64 kids. And so what I'm going to do is I'm going to figure out about, how many of the kids fall within each one of these things. So basically, I'll just count. If I've decided my buckets between 1 and, I know that the ages are between 1 and 16. Let's assume that I already know what the, minimum and the maximum are. Then I figure out, the ranges, and I'll just make a pass through R and count how many are between 1 and 4, how many between 5 and 9. I can do that with one pass, assuming, again, I know what my bucket sizes are. I'll keep a running count. If scanning is not acceptable, these days scanning tends to be very acceptable. If scanning wasn't acceptable, I could use sampling to approximate, pick random values in the data. Actually, sampling is probably more expensive these days than scanning. But I could just go ahead and use things based on sampling to figure out what percentage of the sample fall within each range, and then assume that that's also true for the data as a whole. Okay, so that could be done. Now the question is, if I figure this out, my data changes. I have inserts, updates, and deletes that happen on my data. So I figure out what the histogram is, and let's talk about a couple of different ways that we can go ahead and keep the histograms up to date as kids get added, deleted, ages change, things like that. One thing I can do is just periodically figure out the new histogram. Every day, every couple of hours, when I happen to have free time, I can figure out the new histogram and not worry about the data being kept completely up to date. Another thing that I can do is every time there's an insert, update, or delete, I can change the histogram values as I go, not necessarily always writing it out to the catalogs, but keeping track of it in memory. The tendency has been to do more of the periodic recomputation because keeping the exact histogram, even in memory, usually ends up not necessarily being worth it. Incrementally updating periodically could be worthwhile. Oh, and there are two ways that I can incrementally update. Way number one, I'll just figure out what the new value is by doing a complete pass through the data. Way number two, I have the description of the operations that I've done and what their effect is on this thing. So I'll figure out what the incremental effect of all the updates that I've done is. And that's a way of doing it as well. So how do I use these things? So again, I have a selection where A equals 5 of R, and there are 16 values. So I will, assume that, basically since there are 64, if I know there are 64 values, I would assume that, each of the 16 ages would have 4 things in it. If I'm going ahead and I'm using the equal with histograms, 5 is in the bucket 5-8. Okay. 5-8 has 19 tuples in it. Okay. If I assume uniform distribution, not across everything, but only within the bucket, then there are 19 tuples in that bucket, and there are 4 values. So I'll assume that there are basically 19 divided by 4, rounding up, call that 5. You can actually use 4.75 if I want to. But then I'll assume that the number values would end up being 5. And again, look at the picture, right? So the number that have the value 5 just happens to be something where there aren't that many values in it. So this wasn't a very good answer. It would be a better answer if I was looking for the things that were 6 or 7. So you'll notice again, for 5, you got the value that there are close to 5 tuples in it. We would get the same thing for 6. We would get the same thing for 7. Same thing for 8. It's good for 6 or 7. It's not so great for 5. It's not so good for 8. Anyway, that's what we get. What if we wanted to look for the things where the range is between 7 and 16? Okay, well, 7 and 16 is going to correspond to everything in the buckets 9, 12. It's going to be everything in 9, 12. It's going to be everything in 13, 16. But it's a little bit more than that. So how many tuples are there in 9, 12? There are 27 tuples in 9, 12. How many tuples are there in 13, 16? We know from the histogram there are 13 tuples that sit between 13 and 16. Yes, we have the histogram. But 7, 16 is a partial cover of the bucket that has 5, 8 in it. It doesn't cover all of it, but it does cover half of it. Okay? So 7, 16 is going to cover half of that. So we'll take the 19 tuples and we'll divide that by 2, maybe round it. We'll take 19 divided by 2 plus 27 plus 13, and that's a little less than 50. Again, there's no reason not to use 49 and a half. That's a little less than 50. The actual value is 52. Came up with a pretty good value this time. It varies. So that's the way that this approach works. And again, you have a choice. How did you pick B? You have a bigger value of B, there's more calculation that's involved, more buckets you have to have. And again, you're not going to keep everything for every salary, including pennies involved, or for every time unit, including microseconds or even milliseconds. But pick a bigger value B, you'll get a better estimate probably. But you'll have to keep track of more things and look up more things and calculate more things. So trade-off. Oops. And then there's equal height histogram. And you can probably guess what that one is. Equal width means that all the widths are equal. Equal height means that all the heights are approximately equal. So with an equal height histogram and with the same data that's involved, and sometimes it doesn't work out as exactly as it does in this case, there are 64 different things. What we're going to do is we're going to put things together so that the total number of tuples inside each of our 4 buckets is going to be the same or pretty close to the same. So as it turns out, in this case, I can have 16 things in the smallest bucket, which is the values between 1 and 7. 16 tuples fall into that. Again, it doesn't necessarily always work exactly, right? For example, if there had been 5 people whose age was 7, then it would be an exact boundary. But here, it happens to be that way. The next bucket has 8 and 9, that adds up to 16. The next bucket has, 10 through 11, that happens to have 16, and then another 16 or 12 through 16. So again, if it's not exact, it's still pretty good. Being off by 1 or 2 or a couple probably isn't that big a deal. If you want to, you can keep track of how far off you are. So here what we're doing is we're dividing the domain into B, which in this case is 4, buckets that have the same number of tuples in them. So we have 4 buckets with the same number of tuples, and we store numbers and the bucket boundaries. So we actually keep track of how many things fall inside each of the buckets, which is not always exactly 16. And the idea is that buckets that have, where you have, higher frequencies are more important than, low frequencies. So, basically, there are 7 different values in that first bucket. There are only 2 in the second and the third. And that gives you what often is a better approach than the equal width approach to figuring out what things are. So how do you construct these things? So there's, how do you construct it, how do you maintain it, and how do you use it? Well, it's the same darn thing, except that you need to do a sort to be able to figure out what's going on. So, and yeah, you could play hashing games with this, but it's a little more complicated. The easiest thing is to go ahead and do the sort of all the values, and then take equally spaced things. So if you sort the values as shown over there, then you can say, okay, let me take the first approximately 16 things and put it in bucket 1, and the next approximately 16 things and put it into bucket 2, et cetera, et cetera. And again, you could choose to take an approach based on sampling if you didn't want to do a full scan or a full sort. You could go ahead and sample and then sort based on the sample and figure out what the buckets are approximately. Won't be exactly right, but sometimes that can be a better way of doing it. And it's going to be questions about how you end up maintaining this. Again, you can periodically recompute what the histogram is, what the now equal height histogram is. But also what you can do is do an incremental maintenance approach as new tuples come in, and to be able to play games about keeping this maintained and be equal height. What you can do is deal with your buckets and deal with changing these buckets so that you might move things into another bucket when something becomes too big. So if this bucket had 16 things in it, now it's got 23 in it, I might take the last value and move it to the neighbor to try to maintain, because somebody's got to have fewer. So I can go ahead and I can play games to maintain my equal height histogram, and it's not exactly the same as the B-tree split thing, but you can see that it's playing with the boundaries and moving things across the boundary as necessary when something gets too big or too small. And how do you use it? We're going to take the same 2 queries that we had before, and we're going to see how it works. So if we're doing sigma on A equals 5 of R is going to be in the bucket 1, 7. Going to give away the punchline, which is on the slide. This is actually going to turn out to be better than the equal width approach. So 5 is in bucket 1, 7. 1, 7 again has 16 tuples in it. They happen to work out equally this time. Okay, we'll assume uniform distribution inside the bucket. There's 7 values inside the bucket. We haven't fully gotten away from uniform distribution, but unless we're going to keep track of every single darn value, and we could, then it's hard to get around that. We could keep track of every darn value, but this is a way of, making things a bit better without keeping track of every darn value, because again, there could be a huge number of values. So 7 different values between 1 and 7, 16 things inside the bucket, 16 sevenths, approximately 2. Again, we could actually do it out as something where we figured out as 2.29 or whatever. There's no reason to actually have to have an integer. The actual value is 1. That's a lot better than what we had before. Before we figured out that the value was what, 5 or something like that, when we did it with the, let's actually go back. Before we thought it was 5 when the actual value was 1. Now we think it's 2 when the value was 1. It's not perfect, but it's better. And often, not always, but often height ends up being better. Well, let's see how it goes on that range question before we go.
So When you have something like a bar chart and you're doing this on things like names, are you going to really use the full name, or are you gonna do something like value it by the alphabetic letter A, B, C, D?
Yes, there are all sorts of variations of this that you can use where you can just go ahead and play it with a prefix rather than the whole thing. But basically what you're doing is you're treating everything with a prefix, like the first letter, as if it's another special bucket where you're bucketing, it's a second level bucketing that you're doing. So, you know, do you want to have buckets within buckets and so on? You might want to, but frankly, the whole bucket concept takes care of what you want to do directly. You could do it. It's not entirely clear to me that it adds much value as opposed to just going ahead and bucketing straight. Because, you know, storing, you know, the longer length may not be that big a deal. So if you really want to save, if you're keeping, you know, 1 million buckets, and you want to save on it where you just keep the first 4 characters defining it, you could do it, get the imprecision, but also save the space that corresponds to it. What I like about the question is you're thinking outside the box and thinking about other possibilities. Everything that I'm talking about, every single database system has its own different ways of playing with how to choose, you know, the right ways to do this. And which one is better? I mean, basically, people do things based on what their customers want and what they're capable of programming and maintaining over time as programmers come and go. Maintenance of database software is fun. Maintenance of system software in general is fun. Applications too, but particularly systems. But again, great question. Don't assume that anything that I say to you is exactly the way things are done. It's just opening up the possibilities, and there are many, many more. Let's just take that range query. Okay, so if we have something where we're looking at 7 to 16, it covers completely 3 of the buckets, 8, 9, 10 to 11, 12 to 16. All of those have tuples inside them. It partially covers the 1 to 7 bucket. So those 3 buckets, each of them has 16 tuples inside it. The 1 to 7 bucket is something where it ends up having 16 tuples like all the other buckets in it. But the values inside that match, because we're looking from 7 to 16, it's just one of the values between 1 and 7. So there's 7 values between 1 and 7. So we'll assume that 1/7 correspond, we're doing uniformity within the bucket. So we'll assume that 1/7 of the 16 tuples, you know, get hit with the value 7. So we're gonna take 16/7, which we'll estimate as being 2, it's a little bit more. Plus 7, plus 16, plus 16, plus 16, that coincidentally happens to add up to 50 again, and a little more than 50. But the actual value is 52. As it happens, we got the same 50 we got by the previous algorithm, a pretty good estimate. None of these are perfect. But there's a trade-off between trying to keep all the values exactly. I mean, what the heck? Here's something I expected somebody to say. What if I go ahead and I use a hash function? And I use a hash function to keep count for everything. And I play with using extendable hashing so that as the number of values works, I don't have a big overhead maintaining it. And I can add and I subtract. You know, in an insert, I do an add. When I delete, I do a subtract. You know, that'll work really nicely. But it'll work really nicely for checking for the exact value. If I wanted to find all the things where the value is 5, I hash 5 and I look up inside it. It's doable, but it's painful if I'm looking inside a range. For example, if I'm looking for everything between 3 and 70, I'd have to hash on 3, hash on 4, hash on 5, all the way up to 70. And then add up the values to be able to, I mean, I could do it, but it'd be expensive. But again, if I'm dealing with timestamps or money and it's in cents or even milliseconds, trying all the different values